8. Hypothesis testing. Okay, so in this video we're going to go over hypothesis testing, both the null and the alternative. So we're going to start with what the logic is around hypothesis testing. We're going to talk about how to state hypothesis testing, including the critical regions, how to integrate z-tests and make decisions with the hypothesis testing. We'll also go over type 1 and type 2 errors. And then we'll also talk about calculating Cohen's d, and then once we calculate Cohen's d, what does it mean to have a small, medium, large, extra large effect size with Cohen's d as the calculation. And then when we make a directional hypothesis versus just the customary two-tailed hypothesis testing, or, when we talk about maybe doing like a more one-tailed testing. Okay, some of the logic. Okay, so hypothesis testing is one of the more commonly used procedures that we use in inferential statistics. So when we talked back in the first lecture, we talked about descriptive statistics versus inferential statistics, and the last 2, 3, 4 lectures, we really hit hard this power that inferential statistics gives us, right? This ability to take a small group of scores, or sometimes even just one raw score, but really a group of scores, test it, and then infer back to the greater population about, well, maybe it is this treatment that's making that effect or that change. The definition is that it's a statistical method that uses a sample data to evaluate a hypothesis about a population. And there's a very specific structure we do that with. So we're going to state the hypothesis about a population. Okay, so that's our goal. We're going to try to make a statement, a testable theory about a population. So what we're going to do is we're going to describe the expected characteristics of the sample based on that hypothesis. Okay, and we're going to obtain just a random sample, right? So we have the entire population. Again, we take an authentic random sample from the population, and we compare that obtained sample data with the prediction that was made from the hypothesis, right? And then if it's consistent with the hypothesis is reasonable, if there's a large discrepancy, well, then we can reject that hypothesis. Okay. So basic research situation, we're looking here for hypothesis testing, right? So you have a population parameter. So we have the population mu, right, is known or assumed before the study. So we have that normal distribution. And the purpose of the study is to determine whether the treatment has an effect on the population mean. So again, we have a new medicine we're trying out. We have a new therapy that we're testing on a small group. And we're really trying to find out, okay, it worked, right? Or we have some really good data to support evidence that that's the treatment that's making the effect. Can we then take it back and say, okay, now let's apply this to the population? So on the far left-hand side of the picture there, we have this known population before the treatment. The average is 16 with standard deviation of 3, right? We do the treatment. They go through a research study. And then at the end, well, we don't know, right? So the purpose is through this hypothesis testing, can we make a determination? Okay, so the entire population receives the treatment, then a sample is selected from the treated population. So again, we're kind of grabbing a small group. In the actual research study, however, a sample is selected from the original population, and the treatment is administered to that sample. All right, so the greater population, unknown stuff is going on with that population. We'll then grab a group from that population, and then treat that small sample, right? So in the original one there, you have the known original population, you pull a sample from it. But when we do a hypothesis point of view, or create a structure of a research study from a hypothesis point of view of the test, you take that known original population, treat it, and then the unknown treated population then gives you this treated sample. Sorry, missed one there. From either perspective, the result is a treated sample that represents the treated population. Okay, there's 4 steps to hypothesis testing. And we're going to break these down quite a bit. So I'm just going to tell you the steps really quick, and then we're going to break each one down a lot more. Number 1, state the hypothesis. And yes, you are going to state it in a pair, right? The null and alternative. Number 2, set the criteria for a decision. This is key. You have to set the criteria first and then collect the data and compute the sample statistic. Number 4, make the decision. Okay, so let's break it down. Number 1, or step 1, state the hypothesis. And like I said, this is a pairing, right? So you have a null hypothesis and you have an alternative hypothesis. The null hypothesis is notated with an H sub O or sub 0. And this states the treatment has no effect, no change, no difference, no relationship. It's null. Nada. Bupkis. Nothing. The independent variable, treatment, has no effect on the dependent variable. It's status quo. Right? The alternative, or the flip side, and this is notated H1, and in some academic articles and some journals, it might be notated as H sub A, and that's okay too. It's just shorthand, right? So the alternative hypothesis states that there is a change, there is a difference or a relationship with the general population. Okay, so step 1 is stating if there is no difference, the sample population is just going to act just like the regular population, right? The alternative hypothesis is that there is going to be a change. So null is just flatline, is just nothing, right? If I have a lot of red M&Ms and I don't do anything to them, null, nothing, I still have red M&Ms. If I do something to alter them, soak them in water, right? That red dye is going to come off. So think of alternate hypothesis like something different as I've altered them. My red M&Ms are now, I don't know, at best light pink, but probably just white. Or if I soak them long enough, chocolate and then just peanut. Here's the peanut M&Ms, right? Okay. Step 2, set the criteria for the decision. You have to do this right away. Okay, you can't go back and reset the criteria if you miss your mark. Okay. The distribution of sample means is divided into 2 sections. Those that are likely to be obtained if the null hypothesis is true, and those very likely to be obtained if the null hypothesis is true. Okay. The alpha level, and it looks like the little fish, right? Or the level of significance is the probability value that's used to define the concept of whatever you believe is very unlikely. So think back to last lecture and the lecture before that. So most of the time in social behavioral sciences, your alpha level is going to be 0.05. Okay. So 0.05 if you're running a two-tailed test, which is most of the time, right? So 95%, the bulk of your data is going to be in the middle. Alpha level 0.05 means that you're looking for those 2.5% on both sides, because 2.5 and 2.5 make 5. Those are your extreme or very unlikely. Okay, we call those very unlikely or extreme areas your critical regions. Okay, so your critical regions consist of the extreme sample values that are very unlikely, as defined by your alpha level, to be obtained if the null hypothesis is true. Boundaries of the critical region is determined by the probability set by the alpha level. If the sample data fall in those critical regions, and again, most of the time we are running a two-tailed test. Sometimes you are running a one-tail, but most of the time we're running a two-tail. If the null hypothesis is rejected, and remember, you, the researcher, want to reject that null hypothesis. Okay? Because if you create something, you're hoping that that something has an effect. Right? You're hoping that that treatment cures something. Right? If it doesn't, it's just null. Everything is the same. You are sick. I create medicine. I give you the medicine. If you stay the same, if it's null, the medicine didn't do anything. I want to reject that nullification, right? Okay. So this is what it looks like graphically, right? So the bulk of the data, that 95% middle, if my alpha level is 0.05, the extreme scores right there on the two sides, that's what's shaded in. Okay. So the set of potential samples is divided in those that are likely to be obtained and those that are very unlikely to be obtained if that null hypothesis is true. Okay? So what you have there in the middle, where it's not filled in, where it's just, right, so your normal distribution is in red. So if it's just there in clear, right, those are all your distribution of sample means. So these are not raw scores. These are all groups of sample means, right, close to the null hypothesis. These have very high probability values if the null hypothesis is true. Okay. So if I am somebody who thinks I have a new way to teach people how to do speed reading, okay, and these are all distribution of sample means, so little groups of, I don't know, freshmen in college, and I say I have a new way to teach like speed reading, right? What's the probability of me just randomly selecting a group of people and testing their ability to read, right? Speed read, or the rate of reading. If I grab a sample and their average mean, so a group of 30, and their average reading variability or their reading rate is in the white, it's null. My treatment didn't work, right? But if I randomly select a sample and it's over there on the far right-hand side, meaning that they can really read very, very quickly, right? They are speed readers. Sure, something else might be at play, but it's extremely low probability that something else is making that group of 30 students speed read, right? There's a 98% chance it's my new way of teaching people how to speed read. There's a 2% chance that, I don't know, I just got lucky and randomly selected a group of 30 people that already knew how to speed read. Okay. So again, if the critical region, if you set it, if your alpha level is 0.05, the critical region is your very unlikely outcomes. Most research studies are a two-tailed test. And I'll go into what it sounds like linguistically when we run a two-tailed test, because it sounds very different than running a one-tailed test. A two-tailed test is non-directional, meaning we're looking for an effect, a change. Okay, again, the middle 95% is when you grab a random sample and there's a high probability that null hypothesis is true, that your treatment didn't really have an effect. If your random sample that you pull, though, has a z-score of plus or minus negative 1.96 or positive 1.96, you can pretty confidently reject the null hypothesis with a 95% confidence. And you can say they're falling in that critical region. That is a very unlikely outcome. I'm not saying with 100% assurity, but I'm saying with a really high percent, like 98% sure. It's because of my treatment that I can explain that change, that effect. Step 3, collect your data and run your data. Okay, the data is always collected after the hypothesis is stated. The data is always collected after establishing the criteria. Okay, this sequence of state your hypothesis, collect your data, run your data. It assures objectivity, because if you just collected your data, ran your data, and then set your critical region, you'd always be able to fall in the critical region. You can't do that. Okay? You're still going to use the same formula that we did last week, because you're running it as a distribution of sample means. Okay, so Z is the difference between the observed sample mean and the hypothesized population mean, divided by that same standardized error of the sample mean, right? Or the population mean. Okay, step 4, make the decision. And the decision is always going to be, am I going to reject the null hypothesis, or am I going to fail to reject the null hypothesis? You never say accept the null hypothesis. You only have 2 possible outcomes. You reject the null hypothesis, or you fail to reject the null hypothesis. Okay? So if the sample data is located in the critical region, you can reject the null hypothesis. And you're like super excited because your treatment like had an effect. If the sample data is not located in that critical region, the data did not prove evidence. So you don't accept the null hypothesis because it sounds redundant. So you just say, I fail to reject the null hypothesis. Okay. So this is just a quick analogy. So the null hypothesis is either rejected or the researcher fails to reject the null hypothesis. The process of conducting this hypothesis test is very similar to like a jury trial. So somebody commits a crime and they have to go, it's not just like a speeding ticket and you pay the fee, but you actually have to go to trial. Okay. So a jury trial begins with a null hypothesis. So in the United States of America in the current year, 2024, you are presumed innocent, right? So you are not guilty. And the police and the prosecuting attorneys have to gather enough evidence or data to prove that you actually committed the crime. They have to prove your guilt, right? So in the year 2024, in the United States of America, you are innocent. You are nulled. You are nullified. There is no guilt assumed. And it's up to not your defense attorney, but the other side, the prosecuting attorney, the police, everybody else, to gather data, to gather evidence, to gather witnesses and right, everything else to build a case, right, to build enough data to run the statistical analysis and say, I have enough evidence to fail to reject that null hypothesis of innocence. Okay. With sufficient evidence against the defendant, the jury rejects that null hypothesis, rejects that innocent claim, and says, nope, you're guilty. If they can't get enough evidence, right, so without I don't know, really concrete evidence, I mean, we're talking about like a lot of evidence, right, against the defendant, the jury fails to find the defendant guilty. Okay. But does not necessarily conclude the defendant is innocent. Right? We all can think back on some cases that were like, I wouldn't necessarily say that person's innocent. But the police, the prosecuting attorney, the evidence failed, something, right? It wasn't enough to say without a shadow of a doubt that person was guilty. The same kind of theory holds here with hypothesis testing. And that's what makes it so hard in sciences, both physical and social, to quote unquote prove effectiveness, right? Okay. So let's take a closer look. So the z-score is like a ratio, right? The actual difference between the sample mean and the hypothesized population mean divided by the standard error mean between like mean M and mean, right, M. So we're taking a look at what is the sample mean saying versus like what the population mean is saying, right? So for example, the z-score of plus 3.0 means that the obtained difference, right, this what did I gather difference, is 3 times larger than it would be expected if the treatment had no effect. That's crazy talk, right? That's like exponentially, wow, distance away from the mean, right? It's not just chunk 1, chunk 2, chunk 3. That's like chunk 1, chunk 2, chunk 3, right? That's what I'm saying. So like, yes, in theory, z-scores go on to infinity. And if you ever get a z-score of like 14, do your math again, because you're probably wrong. Okay. Uncertainty and errors in hypothesis testing. Okay, so yes, hypothesis testing is an inferential process. Errors are possible because it uses limited information from that sample that you're gathering of 10, 20, 30 people, right? And it's using that small sample to make a statistical decision. And then from that statistical decision, we're making like a general conclusion, right? So some statisticians don't like hypothesis testing. Well, they have some issues with it, right? Okay, so sample data used to make statistical decision allows to make inferential decisions, yes, but it's more like it helps us draw conclusions about populations. And further testing, or at least repeatable testing, is usually encouraged. Okay, some of the errors that can occur. Type 1 and type 2. Let's start with type 1. Okay, in a type 1 error, the researcher claims to have found something basically and really hasn't. Okay, so the researcher rejects the null hypothesis, and the hypothesis really should have stood. That hypothesis is actually true. Okay. So the researcher concludes a treatment has an effect when there really isn't one. So what's going on here? Well, the alpha level of that probability that test will lead to a type 1 error is probably off. Okay, so adjust your alpha level. Okay, so it determines the probability of obtaining a sample data in the critical region, even though the null hypothesis is true. It usually means your alpha level is too loose, so tighten it up. Type 2 error. So the researcher fails to reject null hypothesis, and they probably should have, because the null hypothesis is false. So this is actually, your treatment works, but you can't prove it, or you didn't prove it, okay? So the researcher failed to detect a real treatment effect. For whatever reason, that sample that they pulled didn't fall in the critical region, even though there really was an effect on most of the treatment, on most of the samples, okay? Type 2 error probability is not easily identified. There's something usually really wonky with that sample that you pulled. I'm going to go back up one slide. If you want to think of it like type 1, the researcher's lying, claiming something that really didn't happen. Type 2 just stinks. It sucks. I shouldn't say that word, but the researcher had it right, but they just can't prove it, right? Either way, run it again. Okay. I like this graphic here. It's just all the different possible outcomes of a statistical decision, right? So you have the actual situation, whatever that is, and there's no effect, and the null hypothesis is true. Sure. The actual effect, the effect exists, and the null hypothesis is false. Sure. You also have some situations where you reject the null hypothesis, and you should have. You have some situations where it yields a type 1 error. Run it again. You have some situation where the decision is incorrect. It could be a type 1 error, could be a type 2 error, which kind of leaves the one up there, type 2. Oh yeah, also, type 1 error is also notated or shorthanded with that. It kind of looks like an alpha, but it's more like just like a traditional Greek letter A. And then type 2 error is almost like a really pretty B, but the tail like drags down longer. So look, top left-hand corner, you'll see the type 2 B. And then you also have like a correct decision, write it like normal. Fail to reject the null hypothesis, yeah, sometimes you should. And then also researcher's decision. Okay. This is just mathematically the location of the critical regions dependent on your alpha level, right? So like I mentioned, in most social behavioral sciences, so your anthropology, sociology, psychology, it's going to be alpha 0.05. So really you're looking for a z-score cutoff of plus or minus 1.96. Rarely you might see alpha level 0.01. Like if you ran it and you're suspecting a type 1 error, run it as an alpha level 0.01. Make your alpha level tighter. And so now your cutoff level is looking for a z-score plus or minus 2.58. If you're really sure, run it as an alpha level 0.001, two-tailed. Nothing's getting past that. I shouldn't say nothing. Everything's statistically possible, but nothing's getting past that. So plus or minus 3.30. Okay, this is the four-step process again. State the hypothesis, pair, and then select your alpha level. Number 2, locate the critical region. Number 3, run the numbers. Number 4, make a decision. Okay. In APA format, obviously, you're going to report your results in a significantly statistically, a result is significant or statistically significant if it is very unlikely to occur, when the null hypothesis is true. And then conclusion, you're going to say, I reject the null hypothesis. You would also report it if you fail to reject the null hypothesis, or you would say the result is insignificant or not statistically significant. And you would also say conclusion, I fail to reject the null hypothesis. Okay. You report any significant effect you find, you report the value of the test statistic, and you also report the p-value of your test statistic. Okay. Some other influential factors to keep in mind, the size of the difference between the sample mean and the original population mean. If you're doing something that has millions of data points, we're talking like SAT scores and GREs, you can just state that it is a normally distributed population. If it's something smaller, but you're dealing with a population, you really do need to state how big the population is. And then obviously how big your sample size is. Yes, the larger the discrepancy between the sample pool that you did and the population mean, it's going to give you a larger z-score. That's okay. Also, a variability of scores. The more variability of scores you have, the larger the standard error. That's okay. It's not going to freak anybody out. They understand that. The number of scores in the sample, also the larger number of sample pool that you have, is going to give you a smaller standard error until you approximate that population, which then you're going to have 0 after a while. Some of the assumptions for the hypothesis test to keep in mind with z-scores, obviously stay true with random sampling. Don't cherry pick your data. Everything should be independent observations. Don't double dip. The value of your standard deviation is unchanged by the treatment. Please, please, please. And then always assume that it is a normally standard distribution, that you're pulling it from a population, or you're having a sample size over 30, so that you can make sure that you can use that unit normal table or your z-table. Okay. Sometimes we get to use a one-tailed hypothesis test. It's okay. I would say 95% of the time we're doing a two-tailed hypothesis test. Okay. So the standardized hypothesis testing procedure is called a two-tailed or a non-directional test because the critical region is divided or split into two. Sometimes the researcher has specific predictions about the direction of the treatment effect. Okay. You want the blood pressure to go down. You want the rate of reading to go up, right? When a specific direction of the treatment effect can be predicted, it can be incorporated in the hypothesis. So usually not. Usually you're looking for an effect, a change, a difference. Okay? In a directional or a one-tailed test, the researcher specifies either an increase or decrease in the population mean as a consequence of that treatment. And it's very obvious in the language how they write the test. Graphically, it looks like this. So remember how like in the previous ones that we had like two shaded parts? Now we just have one shaded part. Okay. You'll note that, okay, so this is still same like alpha level 0.05. It's all in that one side now then. See how your z-score is bigger? Right. So that critical region is a lot easier to hit. Okay. So you're going to reject the null hypothesis if you hit in that critical region. So if you say, okay, what's the probability that I'm going to randomly pull, a sample mean, a group, of sample means, and I pull it, and it's going to be in that critical region. All right, I still reject my null hypothesis if they pull in the critical region. It's a lot thicker though. Okay. A one-tailed test allows rejecting the null hypothesis when there's a relatively small difference in the specified direction. Two-tailed test requires a relatively large difference regardless of the direction. In general, a two-tailed test should be used unless it's a strong justification for the directional prediction. And like I said, it's 5% or lower that you'll see a one-tailed test. Usually, you're going to see a two-tailed test. Okay, effect size. Although commonly used, some scientists are concerned about hypothesis testing, and that's okay. Focus on the test is the data, not the hypothesis. And so significant effects are not always substantial, and that's okay. Effect size measures the absolute magnitude of the treatment effect, independent of the sample size. So at this point, researchers care less about the sample size and more about what is the, I'm trying to think of a word besides magnitude. I already used magnitude. Density. What's the concentration, right, of the treatment effect? Okay. And how we measure that is Cohen's D. Cohen is just the man who invented it, right? Okay. Cohen's D measures the effect size. And it's a very simple way to measure it, okay? You take the mean difference and divide it by the standard deviation. Okay. So you just take the mean of the treatment minus the mean of no treatment and divide it by the standard deviation. It's going to give you a very, very small number. If it's something between like 0 and 0.2, these are ranges. So if it gives you like 2.2, 2.3, it's an ish, right? Small-ish effect. If it's around 0.5, say medium. If it's around 0.8, say large. These aren't like hard and fast numbers. This is going to drive some of you nuts, I know. Okay, so, excuse me. Hold on a second. This isn't trying to these aren't cutoffs. These are like ranges, because what we're trying to find is what's the actual effect? What's the concentration? What's the magnitude? What's the, so take sample size out of it. What's the actual nuts and bolts of this treatment? Is it strong, medium, or large, right? So it has to reach 0.5. If it's 0.48, say it's medium. Don't get too weird about this part. Okay. This is just graphically showing you what it looks like, the different effect, or Cohen's D, of two different situations. So part A, so the top part, the standard deviation is 100, and there's a 15-point effect is relatively small. Versus the second part, part B, the standard deviation is 15, right? So standard deviation is a lot smaller. Now take a look at the 15-point effect. Huge, right? Relatively large. So this whole idea of Cohen's D as the standard deviation helps measure that effect size, or actual effect, or magnitude. Okay, power. Power, you really need to run it before you actually start the study. And it requires a lot of different, or several assumptions about your study. Okay. Power of a test is the probability the test will correctly or accurately make its target. It will correctly reject a false null hypothesis. So it's trying to run it. It runs this analysis before you actually run your test to say, okay, if you do reject a false null hypothesis, you can actually say, yes, I did that. Okay, so it's going to detect a treatment effect if down the road one exists. Mathematically, how you run power is just 1 minus b, or 1 minus the probability that you're going to elicit a type 2 error, right? Or probability of running a type 2 error. We used to run it by hand. SPSS and software runs it now for you. So don't freak out about it. Okay. Yes, okay, so you can run it by hand. You sketch the distribution for null and alternative hypothesis. You locate the critical region and compute the mean. You compute the z-score for both the alternative distribution, and then you find power. But again, we have software that runs for it. I'm going to go back up one. Really what this is trying to do, it runs like a safeguard for you. basically it's a way to like check yourself before you run it, to say, okay, if I do run this analysis and I'm going to get a false null, will you just run this really quick? And if I reject that false null, what's the probability of that? So just run power before you do it. It's fine. This is what it looks like graphically. So left hand shows the distribution of sample means that would be expected if that null hypothesis was true. So your null is on the right hand side, your alternative is on the right hand side. Alpha level is 0.05, right? Two-tailed test, so you're looking for the critical region if you're blowing a z-score of plus or minus 1.96. Okay, so the expected value of the mean is 80. Okay, so the shaded area on the right gives the power for the hypothesis test. And it says at the end, it says, notice that there is an 8-point effect. Roughly a third of the sample means would be in the critical region. And that's okay. Okay, so just a really quick note about power and that size of the sample that you're pulling. Okay, increase versus decrease power. Okay, as the effect size increases, power also increases. A larger sample size is always good, so it's no shock here that the larger the sample size produces greater power. Using a one-tailed test or directional test increases power relative to a two-tailed test, but that's kind of a smaller point. Okay, decreasing power or losing power, reducing your alpha level, makes the test more stringent and reduces power. And then the opposite of the last point. So using a two-tailed test decreases power. Okay. Graphically, this is what it looks like, because the big thing here is the sample size, which again, no shock to you all. When in doubt, pump up your sample size. And I know it's easy to say, hard to do, because keeping track of humans is really hard in a study because we're expensive. Okay, left-hand side shows the distribution of sample means that will occur if the null hypothesis were true. So null hypothesis, think no difference. The treatment effect didn't work. Okay, critical region is defined for this distribution. It's 0.05. Okay, the right-hand side of the distribution of sample means that would be obtained if there were an 8-point treatment effect. Okay, all the alternative distributions are shaded. It's a lot. Okay. Do you see how just by pumping up the sample size to 25, it increased the power to nearly 100% versus when I just had 4 people in my sample? When I just had 4, my power was at 36. When I pumped up 25, now power is at 100. And yes, I know, it's a lot harder to keep track of 25 people than it is 4 people. No. So compared to the previous 2 examples, a 16-point effect has a power of 89%, so a little bit less, but it's much larger than an 8-point effect, which only has power of 35%. But again, we're back down to 4 people. This is a 20-point decrease. We only have 9 people. See what happened to the power? So it's okay. What it's saying is, I'm just giving you a lot of these different images here to kind of show you the fluctuation. What happens when you mess with power, sample size, effect.